Well, once again, welcome everybody to the grade 11 physical sciences session today. And what we're going to do first to kick off today's session, as you can hear, I'm in a really good mood today. So a lot of energy is going to come through from my side. Okay, and one of the reasons why is because this is a very important section that we're dealing with, okay, chemical change. We've dealt with previous units before. Two other units in term 2, and now term 3 we go through the last 2 or 3 units within chemical change. Okay, so last week, just to recap, we learnt a couple of important terms. Okay, we learnt about bond energy. Okay, so I'm just gonna recap from last week. So we learnt about bond energy. Okay, and of course we learned the definition for that is that that's basically the energy required to break the bonds on the reactants so that products can form, and sometimes vice versa when we want to decompose a product to get reactants again, right? That all requires bond energy. Okay, and to share with you just a little bit also as a bit of a recap about the type of bond energies that certain molecules have. If we look at this, I'm going to construct a slightly I'm going to construct a table, but it's not going to be a big table, so it's going to be quite a small table. But I'm just going to take about 4 elements or 4 types of elements bonded to each other. So if I have a bond over here, you guys are welcome to copy this table down as well. If I have the bond, and I have the bond energy. Okay, now sometimes, and the bond energy, sorry, is in kilojoules per mole. Sometimes, depending on the information given, so bond energy is usually either given to you in a test or exam, what the bond is. Okay, and how much energy the bond has. It's usually either given, or in different textbooks might have different, might either round it off to whole numbers or might have a decimal, it's for etc, etc. But I'm going to round mine off to whole numbers for you guys, just to make it a little bit more simpler. Okay, so bond energy. And if you look at the carbon-hydrogen bond, so if I have a single bond carbon to hydrogen, all right, that has a bond energy of about 413 kilojoules per mole. Okay, I'm not going to write kilojoules per mole because I'm stating my table. That's what bond energy is measured in, of course. But if we have a double bond oxygen bond, so you know, that's O2 basically. Okay, that has a bond energy quite high of about 498, so almost 500 kilojoules per mole. Then we have a double bond carbon to oxygen bond. That's also quite high. It's higher than either. It's 803 kilojoules per mole. The last one is an hydroxide bond, which is just oxygen bonded to a hydrogen or hydrogen bonded to oxygen. And that has around the same region as the first two. That is about 464 kilojoules per mole. Okay. So how do we work bond energy out based on what we've just been given? What happens if I want to have a look, okay, at CH4? If I want to have a look at the, because I've got CH over here, so I want to have a look at CH4. Okay, this is my compound, this is my molecule. All right, we all know this to be denoted as methane. Okay, it's the chemical or molecular formula for methane. Okay, or chemical formula as they say. Okay, and for example, I want to look at how much is the energy taken in per mole. Okay, how much? Okay, so it looks like, if I look at it, All right, let me just think about this first. Let me write out the reaction first. If I want to have a look at a reaction of methane and oxygen, so if I take an example for the reaction, I've got CH4, and that CH4 is a gas, and I want to react that with oxygen, O2 gas. Okay, and that should give me product of CO2 gas. All right, and let me see, and water. Yes, and water. That was the other one. And water obviously is given off in the gas phase as well as water vapor. I'm going to balance the equation as well, so just give me a different color. Let me see, that should go there, and then that should go there. Awesome. And I'm fully balanced. Right, now what I need to do is I want to find out what is the energy taken in per mole of CH4 which reacts. Let me just answer that question quickly. Okay, and now I want to work out the energy that is taken in per mole. Okay, which per mole of CH4 which reacts. So I want to look at the CH4 on the left hand side. Now I want to find out what is the energy of it on the reactant side. Okay, the bond energy. Okay, so I'm having a look at the energy taken in per mole of methane which reacts. So the energy on my reactant side, okay, I need to have a look at what is the total energy on the reactant side over here. Okay, so if I look at my table, I have everything I need here. So for my reactants, bond energy, what am I going to have a look at? I'm going to have a look at, well, I've got CH4 and I've got 4 of them. All right, I got 4 CH4s. Okay, so I'm going to take 4 times 413. So I've got CH4. So these 4 of these over there, over there, over there. So there's 4 of them. So 4 times 413 plus, and I've got O2. Okay, I got O2, double bond oxygen, but I got 2 O2s, okay, which makes it 2 times 498, so I got plus 2 times 498. Alrighty, and that should give me a reactant energy of about 2,648 kilojoules per mole. Alright, now I want to have a look at the energy that got released. Alright, energy that now got released. I want to have a look at the product side now. Alright, sorry, square brackets. So here I've got a CO2, so I've got 2 of these double bond oxygens, a double bonded carbon to oxygen, so I've got 2 times 803 plus, and I got, let me just have a look see here, I got 2 times 2 H2O. Alright, so I got H2O, so that's 4 times 464. And that should give me an answer slightly higher to about 3,462 kilojoules per mole. Now I want to have a look at the energy change. Alright, now I want to have a look where at the energy change between my reactants and products. I want to have a look at the difference. Okay, so what I'm actually doing is I'm taking my reactants minus my products. Okay, so now what I want to do is I want to now take the difference between my reactants minus my product bond energy. So I've got 2,648 minus 3,462, and I get a negative answer of negative 814 kilojoules per mole. which means if they ask now, was this reaction endo or exothermic, we can definitely say that therefore this reaction was a exothermic reaction, which leads into my next recap point on those two. Okay, what I want to have a look at now, what is the difference between endo and exothermic. Now remember, just before I go there, a negative sign here indicates a release of energy. Now we went through that last week, and that is that when there is a release of energy, okay, in other words, energy is lost, okay, we know the reaction is exothermic. Alright, and usually exothermic reactions are denoted especially when there is heat given off. Energy is lost in the form of heat. Alright, and then when energy is taken in, when energy is absorbed, that is your endothermic reaction. Okay, so let's go ahead and just go recap those once again, as well as recapping activation energy as well, which we did have a look at. Okay. So before maybe we go to your endo and exo, let's just have a look at this term called activation energy. Okay. Right, now when we talk about activation energy, okay, just to denote the definition again, okay, this is the amount of energy that reactants or that the reactants must absorb. I wrote my A as a D. Must absorb before a reaction can take place. Okay, that's called activation energy, is the amount of energy that the reactants must absorb before the reaction can take place. Okay, and where does this energy come from? Okay, this energy comes from the kinetic energy. Okay, so we have to think about the kinetic energy, all right, of particles. All right, particles have kinetic energy, okay, when they collide with each other. So when particles collide with each other, that's how reactants or reactions rather occur or happen. When the kinetic particle nature or the kinetic nature of particles, okay, meaning when they collide with each other, that's a reaction occurs or takes place. Okay, now if the particles are not moving fast enough, that does mean that the kinetic energy is not sufficient, meaning the bonds that exist, all right, will not break in the reactant molecules. They will not break because there's not sufficient kinetic energy, meaning no reaction will actually take place. How can we rectify this? All right, how can we rectify that little glitch? Well, first of all, the most simple, increase the temperature. If we increase the temperature, the particles will therefore have more kinetic energy, all right, and that insufficiency of kinetic energy could go to sufficiency or even more than enough for a reaction to actually occur. The other option, of course, is to add a catalyst. Now, if my knowledge serves me correct, or my memory serves me correct, I think I touched on catalyst last week, but I can definitely do it again this week as a recap, since I'm recapping anyway. Okay, is that a catalyst obviously is a substance that is added to a reaction, and what a catalyst does is this decreases all right, the activation energy. Okay. Now, when you decrease the activation energy, in other words, not that much energy is required to make the reaction happen. So what a catalyst essentially also does is it speeds up the reaction. Okay, it allows the reaction to take place, but just at a lower activation energy. So it's less time for the reaction to occur. So it happens way or much faster. So we have two different types of reactions that we classify. Okay, and I'm going to do the exothermic one first. So exothermic, basically, this is a reaction which we think about a good way to put this, which gives off. It gives off energy. All right, it either gives off, or another way we can say it also releases energy. All right, and the endothermic is obviously a reaction, all right, in which energy is absorbed, all right, or taken in. Okay, recapping again from last week. Okay, these are your one-line definitions just to understand exactly what's going on. Okay, and so just to give examples again from last week, any exothermic reaction could be classified, or how we can classify an exothermic reaction is anything that reacts with oxygen. Okay, combustion. Okay, combustion reactions. Okay, which are obviously reactions that occur when reacting with oxygen. Okay, occurring with oxygen, and basically that's your explosions. All right, kaboom. That's an exothermic reaction. Energy is released. Then your endothermic reactions. Okay, just an example. Okay, that is when your bonds or your reaction absorbs the energy, okay, and only energy will be released if new bonds are obviously formed. Only then will it be released, okay, but the absorbing of energy outweighs the release of energy. I want to move to also what we did last week. We touched on enthalpy, all right, enthalpy, which is delta H. Okay, so it's classified as delta H, and basically what this is the heat of a reaction. The heat of a reaction. Okay, or otherwise also known as the net energy. Okay, the net energy that is either liberated, released, right, let go, or absorbed during a reaction. And that's the basics of what we touched on last week. Basically, if this energy, all right, enthalpy, if this energy takes place at a constant pressure, okay, this quantity, all right, of energy will be called the enthalpy change. Okay, that's just a little side note there for you to know what it's called. Okay, most of the time these do occur at a constant pressure. Okay, another way to think of enthalpy, if I take delta H here, is think of it as the potential energy. Okay, the potential energy of our products, okay, minus the potential energy of our reactants. So what we're going to have a look at this week is our potential energy or enthalpy diagrams, okay, which can be used to demonstrate a reaction that has taken place either for exo or endothermic, and these graphs is requirement for test and exam purposes. All right, they love giving it. They love giving you graphs and asking you to work from graphs. They love asking you to draw certain graphs as well. It's a very favorable question in test or exam settings. All right, so what I'm going to do, I'm going to draw a basic, what is known as freehand, but it's not going to be really freehand, but I'm just going to draw an unscaled diagram. Okay, here we go. I'm going to start here. So it starts out like this, and I'll label it now in just a second. Cool. Alright, so I'm going to label this graph for you. So basically, this little section over here, okay, this is your, I'm going to use a different color, but you won't use a different color in the exam. You'll stick with the same color. This is your reactants. And over here, this line at the bottom here, is your products. Okay, now obviously I have not revealed to you what type of reaction this is. I've not stated that yet, okay? So, but for this graph, my reactants are on top and my products are at the bottom. So what I'm showing you is that the potential, this is the potential energy over here of my reactants. And over here, somewhere estimatedly around here, is the potential energy of my products. Okay, so we can clearly see my reactants for my potential energy. My potential energy of my reactants is higher than that of my products. Cool. Now, still haven't said which type of reaction this is yet, but don't matter. Okay. What I want to do is I want to extend this line from my reactants quickly. I'm going to extend it in the straightest line possible. There we go. Okay, so this little difference here, okay, which you'll see, okay, this is what's known as your enthalpy change, delta H. Okay, so you will always write it as delta H. You wouldn't write it as enthalpy change, okay, but basically I'll put it for now for teaching purposes. This is your enthalpy change of the reaction. Okay, so this is a potential energy diagram or an enthalpy diagram. Can someone please tell me, based on what I just said about the difference in the potential energy from my reactants to products, is this an endothermic reaction or is it an exothermic reaction? Take a guess if you don't know. I'm allowing you to guess.
Endothermic is release energy.
Did you say endo is release?
Yeah. I'm asking, is it, I'm just confirming, is it release?
No, endo is absorb.
Endo, okay, so then I think it might be exothermic.
Correct. Right? Awesome. This is a reaction, and this reaction is exothermic. It is our product energy minus our reactant energy, always when it comes to enthalpy change. Okay, potential energy of the products minus the potential energy of our reactants. Okay, so in this case we can see our product energy is a bit lower than that of our reactant energy, so we're going to get a negative answer, and our negative value, like I mentioned earlier, does allude to the fact that it is indeed an exothermic reaction as well. Now, we can see that this is a graph that's been drawn, but this graph, obviously, I've left out one key aspect. The distance here between the peak of the curve and the reactant line, which I've just extended to show you, this bit, okay, is called the activation energy. Why? Because this is where the reactants are obviously on the journey or within the process of becoming what? Products. This is when the energy kicks in, so the reaction basically only starts. Alright? Around from when the curve starts, the reaction starts, it's peaked. Alright, and now over the peak, when it comes down from down the peak, basically now the reaction is obviously coming in, it's in full swing, it's obviously coming to an end to form the products. In this case, it's an exothermic reaction. This graph has been drawn, and we can clearly see that that is this over here, this line, wherever that goes on the graph, that would be the activation energy amount, okay? This value minus the reactant value would obviously give you the amount of the activation energy. This graph is not, or this reaction rather, has not been catalyzed. In other words, no catalyst has been used. What happens if they ask you to draw a graph, or on the same graph show how the graph or the reaction, the potential energy graph will look different if there was the presence of a catalyst? What does a catalyst do? A catalyst lowers the activation energy. So here you come, and all you do, I'm going to use a different color just for teaching purposes, is you draw a dotted line. Okay, I'm going to draw a solid line, and then I'm going to erase it. Alright, that little green line over there shows you that I've lowered the activation energy. Right, I've lowered it. That means I've used a catalyst. Okay, I've lowered the activation energy, has now been lowered from over there to about there, means I've used a catalyst, and I've showed it on the same set of axes. And that would be full marks in an exam setting. Alright, so that is for an exothermic reaction. Right, now we're going to draw the graph for the endothermic reaction, how potential energy graph or enthalpy diagram will look for an endothermic reaction. Okay, and we're also going to draw the catalyzed diagram as well on the same set of axes a little bit later. Okay, so how this is going to work is, again, we're going to always have our reactants. Alright, starting out. Alright, I'm going to draw the curve. So, again, always our reactants. Okay, notice how the graph looks a little different. That now the product potential energy is higher than that of our reactants for an endothermic reaction. And why is that? Is that for an endothermic reaction, we know that energy is obviously absorbed. Okay? Energy is absorbed rather in the reaction rather than released. In this case, the release of energy wasn't enough to surpass the absorbed or the absorption of energy for this reaction. Okay, so again, what do? We extend this line slightly all the way through the end for the reactant line. Okay, so I'm going to draw that as straight as possible. And we know from the peak up until this line that we've extended here, okay, which is in line obviously with our reactant or reactants line, point on the graph. Okay, we know that this is the activation energy. So I'm going to try and write it on the... Okay, we know that from this point, alright, from the products all the way through to our reactants, okay, this point here, again, the difference between round about here, more or less, okay, is our products potential energy value. And here we have our reactants potential energy value. So basically, the difference between the two is known as enthalpy. Okay, the change or the enthalpy change of the reaction. Okay, and that is an endothermic reaction. Potential energy or enthalpy diagram or graph. Now what happens now is the same thing. I'm going to use a different color. If now this reaction is now catalyzed, of course we lower the activation energy. Okay, so I'm going to draw a dotted curve. There we go. That basically indicates that I've lowered the activation energy from so you wouldn't draw this line what I'm about to draw in now, obviously here. Yeah, that little difference there. I've lowered the activation energy, meaning that now there's the presence of a catalyst. I've also drawn it on the same set of axes, on the same graph, meaning that I've also followed the instruction of the examiner, meaning I get all my marks. Something else I just want to share with you guys as well, that another name for reaction coordinate is also time. Alright, or the time taken for reaction to happen, but usually time or reaction coordinate is also a suitable name for the x-axis of this diagram. So before I put the graph back up again, to end off or to conclude, right, with regards to exothermic and endothermic, okay, just using the prefixes here, okay, exo and endo, they both have thermic in there anyway. Enthalpy equals to the product energy minus the reactant energy, and basically what that's going to equal is that's going to basically be the smaller value minus the bigger value, which basically gives us a negative value. With endothermic, it's the same thing. We have product energy minus reactant energy, and basically that is now a bigger value minus a smaller value, and it gives us a positive value. And therefore, if we get a negative value, we know it is an exothermic reaction. If we get a positive value, we definitely know it is an endothermic reaction. Awesome. And to end off, any questions? That is all that we have in store for this week with regards to potential energy and endo and exothermic graphs, putting them together, having a look at them together. That wraps up this little section of this unit, and thank you so much for joining me, and I really hope this lesson was informative and that you understood all the content that was taught. Thank you so much for joining me, and we'll see you next week.